Okay, this is a continuation of the first law concept, and that last time we talked about open systems and closed systems. So, first law of thermodynamics. Is presented to us in an equation, delta E equals Q plus W, and this is referred to as the change in internal energy, the net change in internal energy. To be more specific of the system that you are looking at. Now, in determining the net change in internal energy, you have to determine whether the system is an open system or a closed system. If a system is an open system, delta V, or change in molar volumes, does not equal 0, and you have to calculate a work function. And that I've shown is the 2.5 delta V. Apply the expansion compression issue right here. So if delta V is not 0, then you will have a number in this second part of the equation. Here is the Hess's law calculation right here, okay? Or it's attached to the end of the equation. Now, if you're in a closed system, delta V, or your change in molar volumes, is in fact 0. You won't have a work function. When delta V equals 0, then work equals 0. And when you look at the delta E net equals delta H of reaction, the Hess law calculation, plus P delta V, then if you put 0 there, then this term goes out to 0, and the change in internal energy is also the enthalpy of reaction. Delta H is also called enthalpy. Also heat of reaction, and is the Hess law calculation for any reaction that you are studying. Okay? This is the focal point of today's work. Finishing the first law study is closed system reaction. There are 3 cases of closed system reactions such that delta V M is equal to 0. So delta E net, just to repeat this, delta H of reaction plus P delta V goes out to 0, and so the only thing we're measuring in the part of closed system is energy transfer. That's it, heat transfer. So this is A. If the sum of all the changes in molar volume of the reactants equal sum of the changes in molar volume of the products, then delta V will become 0, and that's closed system. Iodine, molecular iodine in a gas phase reacting with molecular hydrogen in the gas phase will make 2 moles of hydrogen iodide in the gas phase, and so you have 2 VMs here, 2 VMs here, and since those are equal, and then delta V is equal to 0, and this represents a closed system. Now this will have, and I don't know what it is, delta H of reaction. So you'll see this. This is just the. This is both the heat of reaction and the net change in internal energy. Since work is equal to, volume is equal to 0, work is equal to 0, and so that's one case in a closed system. Second case is what we call a bomb calorimeter. A bomb calorimeter is a special piece of equipment for measuring heat of reaction without considering the expansion or compression issues associated with changes in volume. Get it up a little bit. So here is the reaction chamber, and there is usually a stage right here connected in through a transformer where they can send electric current through it and ignite the reaction right here. The chamber is flooded with oxygen, and when ignited, it's a combustion reaction for basically whatever you put in there. Okay, and around the reaction chamber is water, if you can see that. Then there's a thermometer, thermocouple, and all you have to do is measure changes in temperature, and they're exclusively increasing and exclusively exothermic. So you can apply this idea to many substances and study how that individual substance undergoes oxidation, and there are a number of other things that you can do. Okay, when you get your bomb calorimeter from the manufacturer, it will have a calorimeter constant with it, which has been calibrated by the manufacturer, and you apply it to the delta H. Q equals delta H reaction, and it's C sub V delta T. And C sub V is your calorimeter constant, which is typically given in the problem that you would be working, and of course delta T is the observed temperature change. Like this, okay? Okay, here I'm giving you, say, a 0.25 gram sample of graphite, and it's burned in the bomb calorimeter or undergoes oxidation. That is carbon graphite as a solid plus O2 gas goes to, say, some combustion products. Okay, and the question is, what's the heat of reaction of this process? Okay, so it's the combustion, the bomb calorimeter equation that calculates your heat of reaction, and you're given the calorimeter constant. Now let's say, I forgot to put temperature change. Let's say observed delta T is 25 degrees C. So that makes it pretty straightforward in terms of just calculating the delta H of reaction. But what you need to note here, and that's why I'm doing this, this is for 0.25 grams of graphite, which is C sub V, which is 210 kilojoules per degree Celsius, times the 25 degrees Celsius, and so I've got a big number here. say 5250 kilojoules, because of course degrees Celsius will drop out in the calculation. But this 5250 is the amount of energy delivered from 0.25 grams. If we need to calculate the molar heat of reaction, we need to divide this number by the mole weight so we can get kilojoules per mole. This number right here, Q, for this reaction is 5250 kilojoules per 0.25 grams of carbon. To get it to moles, you have to convert, kilojoules per mole, you have to convert the denominator to moles, normalize it to kilojoules right here. That's 0.25 over 12 moles. So now you've got it in kilojoules per mole. Very straightforward, but you don't want to find yourself picking the answer just for 2.25 grams or whatever. So that's So that's 252,000 kilojoules. So that's just a direct way of getting the heat of reaction using a piece of equipment. But you have to, again, be conscious of the amount of substances. You're not going to burn a whole mole or 12 grams and then blow the thing. Third scenario for closed systems are solution phase reactions, because they don't have a change in volume of the solvent. Say you run an acid-base reaction in water, well, it starts out at 200 milliliters, it finishes at 200 milliliters, but you had a temperature change when you mix the acid and the base. So solution phase reactions, specifically the ones you'll have to deal with, are aqueous phase reactions, and they delta V of the reaction system is certainly equal to 0, so that qualifies it as a closed system. It's called calorimetry of solutions. It's also referred to as calorimetry or method of mixing. Because what you're doing is you're mixing items at different temperatures, and there's a heat flow results from the mixing of the items. Now, to understand how to calculate changes in energy in a solution phase system like that, I have to first develop an issue called the heating curve. And in the heating curve, here we will take an object from solid phase through steam, and all the changes that it goes through as heat is applied to melt and to warm, to evaporate, and then carry it to a certain temperature, steam. Okay, the heating curve. There's a bunch of stuff in here, and I'll put this online, and you can just copy it down later, but I need you to listen to me and what's going on in this. Here, we're going to take a block of ice, 10 grams of it. We're going to warm it to melting point. We're going to melt it, and we're going to warm it to boiling point. We're going to evaporate it and then raise the temperature. There's 5 heat changes that are going to look at. What you need to do, and this is called the heating curve again. Draw you an axis. On the horizontal axis, this is heat flow that we're talking about, energy in versus energy out, depending on which way you're going, melting or freezing or whatever. And here's some change in temperature. So what I'm telling you in this problem is that we have a block of ice that starts out at a minus 10 degrees. In order to melt something, you don't melt it at minus 10, you melt it at 0 in this case. Okay, so you have to warm this up to 0 degrees. This is why I'm doing this, to emphasize the idea. And so put a little note under here, that's a solid. So a solid's not going to start melting until you get to the melting point. Now, when you start melting the item, you have an energy flow, and the turn actually is being converted into kinetic energy. The molecules are moving faster. But you don't have a temperature change, like from two phases in contact. You'll hear me say that many times. So this is a solid-liquid interface. It's like ice water. You got your ice floating around there, and it cools it down to a certain point and stays there until all the ice melts. And so it doesn't start warming up until all the ice melts. And so here we are at all the ice has now melted. So when you're single phase, it begins to warm again, and so we can draw up to the boiling point. Yeah, there. And so that's 100 degrees, where water typically boils them. And so this is warming the liquid phase. Two phases in contact again, that's your vapor and your liquid, and through boiling, so that's a liquid gas interface, and you're putting energy into the molecules, into the system, but you're not changing the temperature. And two phases are in contact, remember, you don't change the temperature. And then once all of the sample has been evaporated, then you're free to heat it up to whatever. Here's 110 degrees C is the limit. You can go higher than you want, but I put this in terms of tens to make the calculations run a little bit smoother and faster in terms of this. So this is the gas phase. So here we're looking at 1, 2, 3, 4, 5 independent calculations of heat. Okay. And so what we do is to calculate the entire heat change is the delta H total, and this is equal to the sum of all the delta H of individuals. I just put right there values that you calculate, or the sum of all your Q values. You'll see it also written as sum of all your individual Q values, like that. Now, only two equations are needed here. Okay, and the biggest challenge to students in understanding this is when you read the problem, it's determining that it's a temperature change issue, or determining if it's a melting or freezing or boiling or evaporation, condensation issue. Now, if you are dealing with temperature changes, you see here, solid, the liquid, or the gas phase, you can change the temperature. If it's pure condensed phase, is what, but you will use Q equals MC delta T. It's got temperature change in it, in this equation right there. M's a mass in grams, C is the specific heat, and delta T is the temperature change measured. Here's 10 degrees, 100, another 10. So for 2 and 4, right there, these show no temperature changes, so the equation is not going to have temperature change in it. So this is a Q of phase transition is equal to M times the transition constant, delta HT. There is a transition constant for melting. I showed you earlier is 80. I'll show you that again. And this one's 540 calories per gram. So if you've got 10 grams, that's 5,400 calories is going to be needed to melt, evaporate 10 grams of ice. So what we do is we go through here, and each one is an independent calculation. And then at the end, we add up all of the numbers. So let's start here with number 1. So energy change number 1. Okay, it's a temperature change, so I'll use the MC delta T equation, C delta T, and from the data, and if you saw it, we have 10 grams of ice. The specific heat is 0.50 calories per gram degrees Celsius, and we're warming a change of temperature 10 degrees. Okay, so that gives us 50 calories needed to raise the temperature of that 10 grams of ice. Everybody okay on that? Okay, now this takes us to the second plateau right here. Now two phases in contact, no temperature change. Well, then we'll use the Q equals M delta H transition, and delta H in this case is 80 calories per gram. So Q2 will be M times delta H transition, which is called the heat of fusion. And I'll write this out and put it online tonight if you want to. Okay, so we got 10 grams of ice, and it's 80 calories per gram. So you don't have any temperature change issue here. And so the grams drop out, and so you're left with 800 calories necessary to melt the ice. I am not going to be able to get all of this on there, but I'll try to get it. Q3 is another temperature change. That's right here. And we have to warm once the water is completely melted, or ice is completely melted, we warm the ice water up to boiling point. So that's an MC delta T. We still have 10 grams now of ice water that we're fixing to warm to boiling. 1 calorie per gram degrees Celsius. And you can also be given in joules per gram degree Celsius, 4.184. That'll be 100 degrees Celsius. Okay, so 1,000 calories to raise the temperature from 0 degrees to 100 degrees. That's 10 grams of water. Now we need to evaporate it or boil it into the steam phase, and so that bit puts us in part 4 of the curve, and that is a no temperature change, so we'll use M dot delta H. This time is vaporization. So this is the heat of vaporization is what this is called. It's transition constant. And that's 10 grams times 540 calories per gram. It takes 540 calories to evaporate 1 gram of water. So we have 10 grams, so that's 5,400 calories. And finally, I hate to run off up there, okay, but Q5 is a temperature change by 10 degrees, and so we still have our 10 grams of water, and it's now steam, and it's 0.48 calories per gram, and we're going to warm it, say, 10 degrees to 110. So it's only take into account just a small amount of change, so that's 48 calories. Okay, so we've got it for each one of the phase changes, or each one of the heat changes, and so the total is equal to the sum of all your individual Q values, which we add up 50 plus 800 plus 1,000 plus 140 plus 48, and it's in calories. That gives us 7,298 calories. Okay, some problems may ask you convert it to joules, and I give you calories like I just did. All you do is 7,298 calories times 4.184 joules per calorie, and you can make that conversion. I've got 35, and that's joules, or 30.5 kilojoules. But anyway, I think you kind of have the perspective now what I'm talking about. I will not give you a problem on your exam where you have to go through all of those individual calculations. The problems you'll get will involve fragments of the transition here, okay? You might have some water, and as to go from ice, a certain amount of ice, to a certain temperature, and you'll just have to calculate a certain section or fragment of that. So, okay, so we're talking calorimetry problems. Okay, I'm sitting here thinking. Okay, a little change in plan here. And we'll use specific heat of water is equal to 4.184 joules per gram degree Celsius. Now, essentially, what you have to do here is to find issues that are change in phase, in which you'd use the M delta H equation, or not change in phase, just warming or cooling, okay? Now, in this case, and a lot of times it would be helpful to just draw you a picture of what the problem is involving. So let's just say you have a little block of copper, and we're talking about 50 grams of it at 150 degrees C. All right, and we're going to place that into 100 grams of water. I hope I'm not getting too hot. Grams of water at 25 degrees C. What's the final temperature of those items when they come to thermal equilibrium or achieve the same temperature? Well, there is no melting or freezing involved in this thing. You're cooling the copper sample, and you're warming the solvent, water. That's only two issues. So you have the Q that you're trying to calculate is the total, whatever, is the Q for cooling copper plus Q for warming water. And because the first law of thermodynamics says that energy is neither created nor destroyed, the sum of all your Q values is equal to 0. So the sum of all the Q values involved in this transition will be 0. All you have to do, once you identify what's going on, is pick the equation you need for the Q value. So both of them are going to involve temperature change. And if it was a melting or evaporation, you'd insert that in there. And so I'll do one next time in a minute. So what you have is the cooling of the copper. So that's an MC delta T, and we'll put copper right here. That's the temperature change. You're cooling the copper. Doesn't matter whether you put cooling or it doesn't, but you have to identify it as the copper energy change plus the warming of the water, MC delta T for the water. And all that equals 0. Anytime you do this, some of all the energy changes. Okay, so what do we have here? We got the mass of copper is 150 grams.
No,
Specific heat is 0.
It's just 50.
50 grams of copper and 384 joules per gram degree C, and the final temperature is unknown. So when you calculate a change, how do you do it? Final minus initial. So we're looking for the final temperature, so we'll put that in as a variable, TF, like that, minus 150 degrees C. So that's your heat change for the copper. Don't worry about heat loss, heat gain, okay? If you take it the sum of the Q values, you put in the equation, okay, and go T temperature change, T final minus T initial. When you solve the algebra of the problem, it'll take care of itself. Okay, so don't worry about that. And so you have to, now you have to put the water in here. So we have 100 grams of water, and I'll come back down here, 4.184 joules per gram degree C, and its temperature is T final minus 25 degrees C, like that. And all of that is going to be equal to 0. See how it's kind of bobbing from the assumption up here? Okay, move it up so we can finish the calculation. Now, I assure you it's going to come out in degrees Celsius. So to simplify, what I suggest you do once you get this much, take all the units out and set up your algebra. For example, I go 50 times 0.384 times T final, which is the objective, minus 150, okay, like that, plus the water, 100 grams. We got 100 times 4.184 and T final minus 25, and all that's equal to 0. Sorry, plan ahead. So now it's a little easier to manipulate the numbers. So here, let's just do this as 0.384 times 50, and taking it part at a time, that's 19.2 times TF minus 150. All right, that's that part, plus 418.4 TF minus 25. Okay, that's that one, and all that is equal to 0. Then we can distribute and then solve for the unknown. Okay, so we have 150 times 19.2. So this would be 19.2 TF minus 2880. Right there. And we'll just keep the items separate. And that will give you 418.4 TF minus 10,460. All that equals 0. So I'm going to add these two together. So that's 418.4 plus 19.2. So we got 437.6 TF. And then I'm going to add these and transpose it to the right side of our little algebra equation here. So I got 10,460 plus 2880. And I got 13,340. Okay, so TF now is 13,340 over 437.6 degrees C. And it comes out 30.5 degrees C. So that's your thermodynamic equilibrium temperature on when both of them are mixed together. Now the issue is this. The assumption back here, sum of all your energy changes equals 0. You have to be able to identify the types of energy changes that are going on. And that's why it's very important that you try these problems at home, so that you can kind of mentally have the time to study and think about how, well, is it melting or freezing? I'll do one more here on that involves melting. Also, we'll throw some ice and water and find out what the final temperature is. Now, it also can ask you just, and you put copper in at 100 degrees and it winds up at 50 degrees, I don't know. How much energy has changed? So all you have to do is use an MC delta T equation. Okay, and I'll give you the specific heat, something like that. But this needs to be practiced to calculate a final temperature to get comfortable. So we're given 25 grams of ice thrown into 75, let's make it 175. I don't want big changes. We may freeze the water. 175 milliliters of water, what's the final temperature? Okay, and I'll give you the specific heats and transition constants. So the main thing that is important here is that you define what the different energy changes are. Okay, so you have to visualize, and so suggest drawing out again what is going on. So we're taking a block, 25 grams ice, okay, and we're putting it into 175 milliliters of water at 25 degrees Celsius. And the question is, what's the final temperature? Now, in here, three things are going on, believe it or not. The sum of, making a mess, try to keep neat, Q equals, okay, one, you've got to melt the ice. Okay, so we got to, melt ice. Then you have to warm the ice water. So you have not only a melting issue, but when it's all melted, you have just 25 grams of water. It's at 0 degrees. You assume that. You're not going to be told it's at 0, but you know if it melts, it starts at 0 and ends at 0. So this is Q of warming 25 grams of ice water. Now, the other side of the coin, the final part, is the cooling of the solvent water. That's what I call the solvent water. Versus the ice water. So it kind of separates the items so that you can see. So this is cooling of solvent water. Okay. Now decide on which equations you have to use. If you're evaporating, condensing, boiling, or freezing, or melting, and that's two phases in contact, so no temperature change is involved. So this would be a mass times delta H, transition. So the first equation is your mass of your ice times your delta H effusion of the ice. And I'll give you that, that's 80 calories per gram, okay? We looked at that earlier. Now, once everything's melted, we are warming it to the final temperature. Now that is a temperature change problem. So it's MC delta T final minus wherever it initial, okay? So we started, we don't know where it's going, T final, that's the problem. It starts at 0 though. So it's going to be T final minus 0 when I insert the data. So this is ice water. And then you're cooling the solvent water, which is a temperature change, and it's MC delta T, T final minus 25, because your initial was 25 degrees going down to something if it changes. Hopefully it will. So this is your solvent water. So now it's a matter of substituting the appropriate data. We have 25 grams of ice, and it's 80 calories per gram. Plus ice water, so it's 25 grams of ice water once it melts, and that is 1 calorie per gram degree Celsius right there, and it's T final minus 0 degrees Celsius. And then we have the cooling of the solvent water, and we have 175 milliliters, well 1 gram per milliliter, and that's 175 grams. Everybody caught that? Sometimes they give it in milliliters. Water is assumed to be 1 gram per mil, so that's where you get your mass thing here. And that too is 1 calorie per gram degree Celsius, and that will go T final minus the 25 degrees Celsius that you started at, and all of this equals 0. Drop out the units now and solve your algebra. And I'll move it over here a little bit, try to get everybody together. 25 times 80, so that's the ice, melting the ice, plus 25 times 1, TF minus 0, C, and that's the warming of the ice water, and then plus 175 times 1, TF minus 25. And again, all of that equals 0. Right there. Like that. Okay, so what do we got? 25 times 80. And so that is 2,000. And so that's 25 T final. So makes that real easy. And then 175 T final minus 4375, and all that equals 0. So here's your melting, warming, and this cooling solvent water. And so it kind of reduces to a little bit simpler type of equation. And so we need 25, 175 is 200, and then we'll subtract that out, 4375. 4375 minus 2,000, that's 2375. So we got 200 TF is equal to plus 2375, and now TF 2375 over 200 degrees C, and so it takes us down to about 11.9 degrees C. So you went from 25 down to 11.9. Now, how much can you calculate the exact amount of energy lost based on this temperature change? Let's say of ice, yeah. And so if I give you a temperature change, you just multiply that times M times C, and you get just the energy change associated with the ice or something like that. Ice water. Okay. Formation of chemical bonds is always exothermic. Otherwise, the bond would not form. That's the simplest of it. Breaking chemical bonds is endothermic. The amount of energy liberated on formation is called the bonding energy. The delta HB is the bonding energy. That's all the energy. If you're going to break that system up, you have to put in the same amount of energy to break the bond. So the bonding energy is equal to whatever amount you need to break the bond. In the formation of a compound from basic elements in standard state, methane, let's take that. I'm going to run through all the processes that it goes through. Methane, CH4, okay, and from Lewis dot structures we know that this is the two-dimensional form of methane. Right there. Okay, now from the standard state, we need 2 moles of molecular hydrogen in gas form. Move it over here. Plus carbon, graphite, 1 mole as a solid. And that's going to make CH4 in the gaseous form. Now that's the standard state equation because it's basic element standard state. Basic element standard state are always 0. Okay, kilojoules. Now if you put hydrogen gas in a bottle along with some carbon graphite, pencil lead, shook it up, you're not going to get anything. The only way you can get methane is from atoms ready to bond. So what you have to do in this problem is convert the elements to atoms ready to bond. And that's called atomization of the elements. Here we have 4 hydrogen atoms. And so basically we are going to promote them to 4 hydrogen atoms with their little electron hanging out and gas form like that. And we're also going to convert carbon to its gas form with its 4 valence electrons out there ready to bond. So this is C here, gas form. Now this is ready to form methane, and so this forms the methane. This change right here is called the delta H atomization, delta HA for hydrogen, or actually 4 of them. Okay, this one is the delta H atomization for graphite, and this is your delta H of formation, standard heat of formation for methane. And this curve line here is the energy liberated, and it's called the bonding energy, standard state bonding energy in here, like that. You can find the values of the standard state methane, hydrogen, and carbon and everything in the textbook right back here. If I can find, get it to, here's carbon. All right, carbon in the graphite form, if you can see this, is 0 right there. Okay, but when we promote carbon to gas, a single element of carbon with its 4 valence electrons stuck out there, we have to put 716.7 kilojoules into it, into a mole right there. Sorry. Okay, so we start at 0 kilojoules right here, and this will go, and this one's 0 kilojoules also. This one will go to, let's say 716. So this is 716.7 kilojoules. We only have 1 mole of it. So essentially we're going from 0 to 716. So this atomization of carbon right here is plus 716.7 kilojoules right there. Well, hydrogen by itself in gas form is 218. So when you get the atom out here at 218 per atom, when we have 4 of them. So 872 kilojoules endothermic. So this is endothermic to push it to that condition. This is endothermic to get it up to here, right here. So it's the change here is 872 minus 0, which is a plus 872 kilojoules for that one energy change. The heat of formation is standard, and for methane it is minus 74.9 kilojoules per mole. And we only have 1 mole involved in this. Okay, we have everything we need to calculate calculate bonding energy. Draw a line under your standard heat of formation. The sum of all of the individual energy changes here, here, and here, algebraically added together, equals the heat of formation up here. That is, delta H of formation for methane is equal, or in any compound, is equal to the delta H of atomization, or 4 hydrogens, plus delta H of atomization of your graphite carbon, plus your bond energy for methane. And so you put the numbers in, solve for delta HP. It's really straightforward once you see through the layout of it. Okay? Drop through. So we have a minus 74.9 kilojoules is equal to 872 kilojoules right there. Maybe I should put my units in. Minus 74.9 kilojoules right there. Plus 716 kilojoules for the carbon, plus delta H bond energy, total bond energy, when 4 carbon-hydrogen bonds are formed. So the delta HB for methane, CH4, is equal to minus 74.9 minus, well, transposing over, it's all going to be negative. Okay, minus 872 minus 716, it's all going to come out in kilojoules, if I've done this right. So that's 63 kilojoules for all of the CH3. Now, I mean CH4. That's 4 carbon-hydrogen bonds. So if I took for one, the delta H for 1 carbon-hydrogen bond would certainly be 1663 divided by 4 kilojoules. And so that's 416 kilojoules per carbon-hydrogen bond. Now, that's called the bonding energy. Okay. That's going to drive me bonkers. Okay. Given a molecule, say CH3OH, like that, what's the total bonding energy? I got 1 minute to calculate. Well, you'll have this. And what this involves is 1, 2, 3 carbon-hydrogen bonds, 1 carbon-oxygen bond, and 1 oxygen-hydrogen bond. Of course, you'll have the table attached to the quiz, to your exam. So what you do is you go in here and you look up the carbon-hydrogen bond, 411. Well, we figured 416 in our little flow chart, but thermodynamic tables are small changes and they think. So each one is 411, so I want 3 times 411 kilojoules. Carbon-oxygen now, so I look up carbon and oxygen's 358 kilojoules. So it's 1 times 358 kilojoules. And 1 oxygen hydrogen, so I come in here, here's hydrogen, there's oxygen and hydrogen right there, that's 459 kilojoules. So if you got the table, all you do is add these up and you'll have the total bonding energy. All right. if I did that right, the total bonding energy of methyl alcohol is 2,050 kilojoules. Well, it took me 2 minutes.